Okay, so this is chapter 6. We're going to be taking a look at the cardiovascular system, focusing in on blood. So the heart basically pumps about 75 milliliters of blood with each contraction. And so you do, like we said in the last chapter, about 70 beats per minute, roughly. So if you multiply those two together, essentially, when you're looking at the amount per minute, you're basically about five-ish or so liters of blood being pumped out per minute. So 75 milliliters per beat, 70 beats per minute is about 5 liters or so. And so essentially, you have your entire blood supply turned over for the most part each minute. And so when you take a look at the functions of the blood itself, and so let me just make sure I got everything set up here really quickly just to make sure everybody is okay here. So it looks good. So first of all, and number one is you have transport. So you're basically going to be transporting your blood, nutrients, waste, and carbon dioxides, and of course hormones to essentially regulate. That's the piece they talk about here with hormones of the activities of the body. And of course, it's also going to be defense. So the defense is going to be the movement of white blood cells, for instance, throughout the body. Of course, antibodies are circulating as well in the blood, and also to reduce fluid loss, for instance, by blood clotting, so that you don't lose blood and fluid. And so those are some of the major pieces. The regulation component, a good one, is not just the delivery of hormones for regulation purposes, but also direct regulation in the sense of maintaining body temperature. And so ultimately what will happen is you regulate, your blood is hot, and so you can basically offload that excess heat with your blood that regulates your core body temperature. You also have osmotic maintenance. So for instance, your salt water balance is going to be regulated by your blood, and also your pH is going to be regulated by your blood in order to keep your internal pH or physiological pH roughly around 7.4. So let's take a look at what's in the blood. So blood is considered a liquid or a fluid connective tissue, and it's made up of obviously the fluid part of it, which we refer to as plasma. That's the fluid piece. And it also has cells in it. So the cells we refer to as formed elements, right? So the formed elements are basically the cells and other sorts of things that are produced by and large by the red marrow. And you have two dominant types of cells in the blood. The first one you're going to see are the red blood cells, or the erythrocytes. These basically will come from stem cells in your bone marrow. And of course, you have white blood cells, or leukocytes, which will also come from stem cells in your bone marrow. So that's basically where they're being made. And as part of this group of white blood cells, you also have platelets. So platelets are actually considered part of the white blood cell group. And so we talked a little bit about that earlier. And so this is kind of what it looks like. So when you're taking a look at the origin of blood cells, basically how they come to be, you can see that first of all, they all start off in the bone marrow, typically of your large bones, your femur and your humerus in particular, but your femur certainly, and your tibia. And they start off with stem cells. So the important thing to understand about stem cells is stem cells essentially are the originating cell for all of the cell source in your body. So all the cells in your body that get replaced have to be replaced by a new cell. And so the original source of those new cells are stem cells. So what stem cells do is they divide to create two cells that are identical to it. One of those becomes a replacement for the stem cell. The other one then becomes some other cell, whatever you need, right? The needed cell. And so these stem cells will basically divide, and then they'll create these different cell lineages. For instance, they'll create what's called erythroblasts, which will develop into red blood cells. And then they will develop into another type of stem cell, different types of blast cells. So the lymphoblasts will become lymphocytes, the monoblasts will become monocytes, the myeloblasts will become three different types of cells called neutrophils, eosinophils, and basophils. So these are just different types of white blood cells. And of course, the megakaryoblast will become platelets, so little chunks of the cytoplasm of the megakaryocyte will essentially create what's called the platelets. So you can see this lineage. This is all happening in your bone marrow. So you can kind of see this lineage that's basically being handed down. So your blood plasma is overwhelmingly composed of water. So blood plasma basically is 90-ish or so percent water. And then also in that you have dissolved stuff. For instance, different proteins that are in there, globulins, fibrinogen, different ions, hormones, those sorts of things. They're all in there. And that makes up less than 10% of the overall plasma. Then you kind of have this like little white layer, which we oftentimes refer to as the Buffy layer. And then you have your formed elements, right? So that's the large packed cells underneath. The other solutes that you have, so for instance, nutrients, waste, gases, hormones, vitamins, that makes up about 22% or so of the overall weight of the plasma. And so generally speaking, your plasma is the fluid portion of your blood. It'll be what regulates your osmotic pressure of the blood. The salts will act as buffers in there. You have different solutes dissolved in your blood plasma as you're moving it back and forth. You have plasma proteins, right? So basically, this is the most abundant thing that you have. Most of them are going to be made by the liver. And what they do is they create osmotic pressure. So this is part of the reason why you get that osmotic pull in the capillary toward the end of a capillary bed, is because those leftover plasma proteins basically kind of make for a more concentrated blood, which then has the effect of pulling the water back into the blood itself. So some of those plasma proteins, for instance, are things like albumins, which are basically shuttle proteins whose job it is to move things back and forth, lipids in particular, throughout the blood. So the albumins are the most abundant of all these plasma proteins. They're going to be made in the liver. And so generally speaking, their job is to transport molecules. So they're basically shuttles, moving stuff through the blood. The other big source of plasma proteins are globulins of different types. So for instance, immunoglobulins form and they fight pathogens. So for instance, antibodies are in this group of globulins. And then of course you have fibrinogen, which is basically an inactive form of the protein fibrin, which essentially is responsible for forming clots whenever you need them, in conjunction, of course, with platelets. Okay. So that's just the basic rundown of the different pieces of the blood. So essentially, when you take a look at red blood cells, they're transporting gases. So we're going to take a look at this, and we're going to focus in on red blood cells here. So typically they have what's called a biconcave shape that increases surface area. So that's kind of what you're going for there. And it's unusual in the sense that they have a kind of a slightly different internal structure. They basically have no nucleus. Every other cell in your body has a nucleus, but not red blood cells. And you have a lot of them. And the reason why they don't have a nucleus is because essentially they're full of the protein hemoglobin, which is the protein that's responsible for binding to your oxygen. So when you take a look at hemoglobin, then is you really have a system here that's really like differentiated and really, really torqued out for oxygen transport. In particular, the protein hemoglobin is also really perfectly created for oxygen delivery. So generally speaking, this will bind to your oxygen. And then what'll happen is that'll turn your blood red. So oxygenated blood is bright red. And deoxygenated blood is kind of more of a bluish color. And so this is a good thing. Having bright red blood means you have oxygenated blood. Now, in hemoglobin, which is essentially what's called a tetramer, so you have 4 major protein subunits, 2 what's called alpha globulins, and 2 beta globulins. And in each of these is what's called a heme group. This is basically a prosthetic group. It's not part of the original protein. It's actually vitamin B12 derived. And it basically forms like this little piece inside each of these globulins. And in the middle of the heme group is complexed an iron atom. And this iron is what binds to the oxygen. So it allows you to bind to your oxygen. And when it's bind to oxygen, it's called oxyhemoglobin. However, hemoglobin can also bind to carbon monoxide, which is the reason why carbon monoxide kills us, is because it competes for the same site as oxygen, and then we can't get oxygen to our system. So when your oxygen leaves hemoglobin and it's deoxygenated, we call it deoxyhemoglobin. So we have actually have terms for these. And it's kind of what they look like. These are actually real micrographs. This is a scanning electron micrograph of the red blood cell. So you can see it's kind of got this little biconcave pucker to it. It's like a little divot right there in the middle. And they're pretty small. So typically when you take a look at a capillary, remember capillaries are really, really tiny cells. And a capillary basically is about the width of one red blood cell. So you basically are moving in through these capillaries in single file. That's how these red blood cells are moving through the capillaries. What this does is it ensures maximum contact with the red blood cell to ensure you have good exchange at the capillary. So here's your hemoglobin. So here you can see your major globulins, right? So you have alpha on these two sides, and you have two betas, the purple ones. And in the middle, you can see this little heme group where you see the red ball is iron. And it's the iron that will bind to the oxygen. So you can see that the hemoglobin has 4 different places for oxygen to bind. So that's basically how we transport oxygen into and around the body. Now, what about carbon dioxide? How do we get carbon dioxide through the body? Right, because that's another thing the blood has to do. It has to pick up carbon dioxide of the tissues and bring it to the lungs to get rid of. Well, there's 3 major ways that you can actually move carbon dioxide. The first one, and probably the least effective, is to basically just have the CO2 transported and dissolve it directly into plasma. This is sort of similar to dissolving CO2 into, say, for instance, Coke, a bottle of Coke, right? Just let it dissolve in there. It will at some point, but it's a very low percentage. It's not a very helpful. It doesn't want to go into solutions, but you can do it a little bit. The other way that you can do this, and this is about roughly a quarter of the CO2, is it will actually bind to the globin part, right? That is the protein portion, not to the heme group of the hemoglobin. And when it binds to the hemoglobin, so here's your hemoglobin. So you basically have your hemoglobin, which is bound with the heme group to all these oxygens. The CO2 will actually bind to a part of the actual protein portion of the hemoglobin. When it does, we refer to it as carbaminohemoglobin. So that's basically a hemoglobin that's carrying CO2s. And so that'll get you a little bit more. But the really big one is what's called the carbonate buffer system. So it's oftentimes transported in the bicarbonate form. And so this is basically what it looks like. So here's our carbonate buffer system. This is essentially what maintains our pH. And so typically if you take a carbon dioxide and add it to a water, it's going to turn into carbonic acid. Now then, just like we saw about in the acid chapter, acids will dissociate, carbonic acid will dissociate into hydrogen ion that creates acidity, and also the bicarbonate ion. Remember, this is a reversible reaction. So if this gets too acidic, we can reverse this reaction to sort of regulate our acid. But since we're adding CO2 into the system, we can basically pack the CO2 into this carbonate system. And that's how almost 3/4 of our carbon dioxide is moved throughout our body. Okay. So typically all of our red blood cells, not typically, absolutely, all of our red blood cells are going to be made in the red bone marrow. And so ultimately what happens in the process of the development of red blood cells is that in order to make room for extra hemoglobin, they basically will kick their nucleus out, as well as most organelles. So essentially what you have is essentially a little sac of hemoglobin. That's pretty much it. So you don't have a nucleus, so you can't make any more proteins, you can't do any cell repair, can't do anything of that. So you don't have anything to really go with. You're just basically a sack of hemoglobin proteins, and so as a result, you have a shelf life of about 120 days, roughly 3 to 4 months. Okay, and so generally speaking, once that 120 days comes, you are particularly old and worn out, and so you are oftentimes removed from circulation, and you are recycled. So typically, you'll have macrophages, where we talked a little bit about those. Those are the white blood cells that will patrol around your body, and they will basically gobble up different things, not just pathogens, but also cell debris and old cells. And what they'll do is they'll break them down. And so you see macrophages in the liver and also in the spleen. And so that'll break them down and recycle them. So when you have your disc-like shape, it allows for maximum surface area to give you really good diffusion and exchange. Now, the hormone that's responsible And by the way, you can get that flexibility. You can get that sort of bendability of the disc shape because you lost your nucleus. So because you kick out your nucleus, it allows you to be a little more flexible so that you can basically kind of bend and flex and get you more surface area. So erythropoietin is essentially the hormone that is produced by the kidneys. And it happens, the triggers when oxygen levels are low. Now, this is the one that will essentially come into bone marrow and it'll basically stimulate bone marrow to start making more red blood cells. So this is the hormone that's responsible for making more red blood cells. So for instance, if you take a look at step one, where you have low oxygen in your blood, it's going to go to the kidneys. It's going to be sensed, first of all, right? So you have sensation, sensed by receptors. It's going to go to the kidneys, and that's going to increase erythropoietin, or EPO, oftentimes it's abbreviation, and that will go to the bone marrow to stimulate the stem cells to start dividing and differentiating into red blood cells, which will then dump into your blood and will bring more oxygen binding capacity to your blood, and it'll bring your blood oxygen levels up. So what about some disorders associated with this? So what happens when things don't work? So jaundice is essentially the accumulation of heme in the blood. And you basically get the accumulation of heme due to red blood cell breakdown. So old red blood cells that get broken down, you recycle things. And so you recycle the heme. So the heme itself is kind of a yellowish color. And so it'll be broken down into this yellowish color. And so if you have an issue with your blood vessels or with your liver, cannot get rid of it, then it backs up into your bloodstream and it starts turning your blood yellow, and you start getting a yellowish look to it. So for instance, your skin and the whites of your eyes start to turn yellow because of this heme buildup. Anemia, which is basically simply just too few red blood cells, or too few functional red blood cells, or too little hemoglobin. Basically what happens is you're not able to bind oxygen normally, and so you don't have enough oxygen delivery. So there's a lot of different types of anemia. One that we run into is like iron deficiency anemia. This is the most common one because of our nutritional deficiencies. Basically, this is if we're not getting enough iron. So you don't have enough iron to make the heme group. So you can't make hemoglobin. And if you can't make hemoglobin, you can't bind oxygen. That's easily fixed. You just basically take an iron supplement and typically you'll be okay. Pernicious anemia is associated with the lack of B12, which is needed to make red blood cells. So basically, you can't make your heme group. Remember, the heme is that little prosthetic group, and it's complex with an iron. So iron deficiency, you make the heme just fine, but you don't have an iron to bind to oxygen. In pernicious anemia, you don't have enough B12, so you can't make heme. It doesn't matter if you have good iron. If you can't make heme, then you're not going to be able to make the prosthetic group to be able to bind to your oxygen. Folic acid deficiency, basically folic acid, which is another vitamin that's involved. It's another B complex vitamin that's also involved in heme production. So you won't be able to make any heme. Genetic disorders. First of all, let's finish with the other anemias, one of which is genetic, not both of them. But hemolytic anemia. So hemo basically means blood. Lytic means cut. So this is blood cutting anemia. This is basically when there's too much hemolysis. So hemo, blood, lysis, cut. There's too much blood cutting. This is the rupturing of the red blood cells, often due to osmotic imbalance. So fresh water in your blood, for instance, will cause massive hemolysis, and you'll get hemolytic anemia because it'll burst all your red blood cells. Sickle cell anemia is a genetic disorder. It's basically a malformed beta globin. So it's malformed, and it creates this sort of sickled cell that is not able to transport oxygen sufficiently. So let's go ahead and take a look now. That's the red blood cells. Now let's take a look at the leukocytes, or the white blood cells. So the white blood cells are normal cells. So they're large cells, they have a nucleus, they've got their organelles. Oftentimes they're translucent unless they're stained, and then they'll be kind of a purple color. There's not nearly as many of them as red blood cells. Most of the formed elements in your blood is basically red blood cell, but they're also produced by the red bone marrow by a different group of hormones. Typically, they're governed by a type of hormone called a colony stimulating factor. This basically stimulates cells to grow in numbers. And if they're all in the same place, they'll form a colony. So these are important because these are immune defenders, right? These are your trained military to protect you. And so some of them will last for days, some for months, some for years, it depends. And so these are the main types. So you can break these guys into major groups. For instance, the top three here, neutrophils, eosinophils, and basophils are what's called granulocytes. Basically, what a granulocyte is, if you take a look at it, is you'll notice that a couple of features of them. First of all, you'll notice these little granules, these like little circles. Those are basically molecules, proteins in some cases, different types of molecules that are basically aggregated in these like little granules in the cytoplasm. And those granules are important because those are molecules that are involved in the immune defense process. Okay. The other thing that they also have is they also have a multi-lobed nucleus. So you can see how you can see a lobe here in the neutrophil. There's a little bit of a constriction, a big lobe right there. There's another little constriction, and then another lobe there. So it's got three major lobes in the neutrophil. Same thing's true for the eosinophil. So you can see a major lobe here, little constriction, and a big lobe right there. Same thing for the basophil as well. So these are called the granulocytes. So they communicate and they organize their activities with these cytoplasmic granules. Then you have the what's called the agranulocytes. So the agranulocytes are basically the lymphocytes and the monocytes. So the lymphocytes basically come in two forms: B and T cells, which typically fight cancer, viruses, things like that. They make antibodies. And the monocytes basically will ultimately become macrophages, and they're phagocytic. So they'll gobble up pathogens, bacteria, and stuff like that. But you can see that a monocyte is basically clear in the cytoplasm, but it has a nice uniform, even if it's kind of a horseshoe shaped nucleus, but it's not puckered, doesn't have those constriction points like the granulocytes have. And lymphocytes typically have a large, kind of an unlobed nucleus itself. So these are your major groupings. So the granular leukocytes are the neutrophils, eosinophils, and basophils. Of course, the agranular leukocytes are going to be the lymphocytes and the monocytes. So let's take a look at each one and what they do. So the neutrophils are the by far most abundant of all the white blood cells. They can form up to about half to almost 3/4 of your overall white blood cells. They tend to have that multi-lobe nucleus, like we mentioned before, and they are phagocytic, which basically means they engulf pathogens. They are also the first responders, so they're usually the first ones on the scene during bacterial infections. And they can leave the bloodstream, so they're found in interstitial fluid in the tissues and also in the lymph. And the important thing is neutrophils, basically, they kill like a bee, which means they kill once and then die. And so when they die, they just basically lay there where they died. And then if you have a big infection, then you'll just have a whole cluster or group of neutrophils just kind of piled up there. And then that becomes what we know as pus. So when you start to get that kind of white pussy look, those are all dead neutrophils that have killed, and they just sort of laid there as they're basically doing battle with the bad guys. So that's kind of what it looks like. So here you can see white blood cell movement kind of oozes into and out of the red blood cell. So here you can see a white blood cell kind of scooching itself out, kind of squeezing itself out into the connective tissue, and then it can kind of patrol the connective tissue. So that's a common white blood cell sort of a thing. Let's take a look at the eosinophils. Eosinophils typically tend to be bilobed, so they have basically two lobes or a nucleus. They have large granules. They tend to stain red, so they look reddish in nature oftentimes. We usually see eosinophils kicking up when we have a parasitic infection, or as a counter against inflammation. So we'll see eosinophils showing up in those cases, but they're not very common. Except in those scenarios. Basophils, which is the last of the granulocytes, are the rarest of all the white blood cells. They have kind of a U-shaped or a lobe nucleus. Oftentimes, you'll find these guys in connective tissue. And so mast cells and basophils are kind of like cousins of each other. So they're very similar to each other. Both of them will release histamine during allergic reactions. And what histamine does, it dilates blood vessels, but it'll constrict breathing, right? This is the reason why in an asthma attack, histamine will shut down your breathing. And so you take an antihistamine to keep those airways open during an asthma attack, but you dilate the vessels to basically allow for more blood flow. That's so that other white blood cells can come to the site of infection and do battle with the bad guys. Now let's take a look at the agranulocytes, right? The ones that don't have these cytoplasmic granules that they use to communicate with each other and that they release. So lymphocytes are usually between a quarter and a third of all your white blood cells. You have two of them. You have a B cell lineage and a T cell lineage. The B cells, when they're mature, are the ones who are responsible for producing antibodies. Okay, and so basically, this is kind of the way your immune system remembers a pathogen, so that it can attack it more efficiently the next time you get infected. So antibodies is sort of like your immune system remembering what it did in order to beat the bad guy. T cells, typically, they directly go after pathogens. So rather than lobbing antibodies at them and killing them with antibodies, they actually go after them and do cell-to-cell combat. And so those are two very, very main and very high profile types of cells in the immune system. And then we have monocytes, which is the largest of the white blood cells. And so these guys are cruising around tissues everywhere. They develop into macrophages when they move into the tissues. And then those macrophages will engulf pathogens because they're phagocytic. They'll also engulf old cells, get rid of those when you need to recycle them, and also debris. So like whenever you injure yourself, let's say, for instance, you cut your connective tissue and there's a lot of connective tissue debris, or you get a bruise, and what happens is you got blood spewed all over your tissues. Then what happens is the macrophages will come in and they'll phagocytize the blood cells and clean it all up, and then they'll clean up all that tissue that's just sort of a debris field, clean the area up so that it can be repaired. So what are some disorders of white blood cells? Well, one is SCID, severe combined immunodeficiency syndrome. It's an inherited disease, basically, where your lymphocytes don't develop, which is a really, really bad thing. So this is basically requires you to live in a bubble or an immune-free environment. You can't interact with the rest of the world because you don't have lymphocytes to fight off the bad guys. Leukemia is a large spectrum group of cancers, liquid cancers, in which your white blood cells proliferate without control, and they get basically kind of out of control. And so generally speaking, when they do, these are not normal white blood cells, they're abnormal. So they don't really function the way they're supposed to. So they just become a really big problem. And it can be quite deadly. And you have infectious mononucleosis, like for instance, Epstein-Barr virus, which is essentially is what goes after lymphocytes. And it makes you fatigue, we get a chronic sore throat and swollen lymph nodes all the time. And so it kind of lasts forever. So those are some examples of some diseases of the white blood cells. Now let's take a look at platelets and blood clotting. So platelets, basically thrombocytes, are essentially fragments of larger cell called megakaryocytes, which are also made as part of the white blood cell developmental lineage in red bone marrow. So platelets themselves are not true cells. So basically they're chunks of cells. And you have about, a couple 100 billion platelets made per day. And of course, it depends. I mean, if you're doing a lot of blood clotting, you're probably going to make more to replace it. But their job is simply to clot the blood or to coagulate the blood. And that's their job. Now, there's certain plasma proteins that will be involved in this. For instance, prothrombin is involved in this process of clotting. So is fibrinogen, which we already said was one of the plasma proteins that we already have in plasma, is also involved in blood clotting. And another vitamin K, is necessary for the formation of prothrombin. So vitamin K is something that you get in bananas. So with blood clotting, what happens as you blood clot a particular, a wound in your vessel, like you have a breach basically in the closed system. Because remember we said the vascular system is a closed system, so the closed vessel system. And so the idea is to keep from leaking all of your blood out. So you basically start blood clotting and patching up that hole. And you have 13 different types of clotting factors. Calcium is one of those. There's lots of different proteins. And so when the vessel breaks, what's going to happen is the platelets are going to clump in order to partially seal. It's going to be a soft little plug. And so what happens is the platelets will release clotting factor to recruit help. And these clotting factors, one will be prothrombin activator, which converts prothrombin into thrombin. And this requires calcium ions, so you need your calcium for this to work. And then once you have thrombin, you turn thrombin on. Basically, it will convert fibrinogen into fibrin. And fibrin is a thread-like protein that acts like rebar. It'll basically kind of form a mesh-like, gauze-like framework that traps all of the red blood cells and things like that and starts to plug things up. And then the clot is pretty solid, much more so than the platelet clot. And then in order to break up the clot, we have to have plasmin come in and destroy that fibrin network so that the tissues can grow and repair once you stop the bleeding. And so this prevents the serum, that is your plasma, from escaping from your system. But sometimes it will escape from the clot. It'll ooze through the clot. So, and when that happens, you'll kind of get that little kind of fluidy oozing effect that you see oftentimes with different types of injuries. And so ultimately, your serum will have all the components of the plasma except for fibrinogen and prothrombin. So that's kind of what it looks like. So first of all, your blood vessel is punctured. Now, in order to keep from bleeding out, your platelets will immediately glom onto and form a platelet plug. So that's the first piece. Then what you want to do is kind of solidify that a little bit because platelets are soft. And so what's going to happen is prothrombin activator will turn on prothrombin, which will then convert fibrinogen into fibrin. And those fibrin threads will then come in and interject into this plug and seal that plug up very strongly, trapping blood vessels and other platelets and things like that. And so that's your clot. That's kind of what it looks like. This is actually a scanning electron micrograph of a clot. So you can see how these little fibrin threads here, these little fibrin threads have trapped a lot of red blood cells in there. And so you've effectively clotted up that hole. Now, what about some disorders? So what happens if the blood clotting goes wrong? Well, the first one we have on our list is thrombocytopenia. This is basically when you have too few platelets. And so because you don't have enough from the bone marrow, this oftentimes is a problem with blood clotting, so you can bleed out. It typically will cause excessive bleeding, even under minor situations. This can be caused by leukemia, or it can also be caused by different types of drugs as a side effect. You also have thromboembolism, we were talked about, right? Where this is basically a thrombus, a stationary clot that forms when and travels. So that's the embolism. And then it plugs another vessel. So that's a clot, basically, is what that is. It's a traveling blood clot. So that's one disorder. And then we have the hemophilias, right? So this is actually, hemophilia means blood lover. So hemo is blood, philia is love, blood lover. So hemophilia A and B, these are issues associated with clotting because you've lost a clotting factor. So you have hemophilia A and B, the von Willebrand disease. Basically, because you lost a clotting factor, you're losing a key player in the ability to form a clot, which allows you to not form a clot. And then essentially you can bleed to death from very minor sorts of things. That's the danger of hemophilia. So let's take a look at some of the blood types we're going to see here. So when we take a look at blood types, we can see these are determined by the proteins on the surface of red blood cells. And so the important thing about those is that when we do blood transfusions, our blood types have to match. And so this is actually how we determined that blood types were important. is because when we tried to transfuse blood, what we noticed is that going from one person to another person, it worked sometimes and sometimes it didn't work. And so what we realized was that we had to make sure that these blood types matched, because if they were compatible, then they would be okay. But if they were incompatible, they would create what's called agglutination or clumping of the red blood cells. Basically, they would kind of clump together. And we're going to talk a little bit about that here in just a second. So first of all, what we noticed is of all the blood groups, we noticed there's a couple of different things to these blood groups. First of all, the ABO blood group is driven by what we refer to as an antigen. And an antigen is any kind of a foreign substance, typically in this case, a glycoprotein, that will trigger an immune response. And the only reason why, and first of all, there's lots of these on cells. Okay, it's not like you just only have one glycoprotein. There's a lot of glycoproteins on cells. It's how cells identify each other. And so there's nothing unusual about a glycoprotein. The only reason why we're following blood type is because this particular set of glycoproteins caused an immune response. So it acted like an antigen. And so when we took a look at the blood types, what we noticed is that there's two different types of antigens. There's a type A antigen and there's a type B antigen. So basically two different forms of the glycoprotein. Which gives us four different blood types. For instance, a person with type A blood has the A antigen or the A glycoprotein. A type B person has the B antigen or the B glycoprotein. An AB person has both the A and the B, and an O type person has neither. And so those are our four major ABO blood groups. So here's what it looks like. So on the surface of an A-type person's red blood cells are the A-type glycoprotein, which you can see here represented as little circles. Now, as a result, the antibodies that they make is basically, and this is true for the immune system, your immune system is only going to make antibodies against what it doesn't know. So for instance, if you have A-type antigen on your red blood cells, your immune system grows up with that and is familiar with the A-type antigen. So it's like, it sees that, and it's like, I don't have a problem with that. However, it does not know what B-type is. And so as a result, it makes antibodies against the B-type antigen. Same thing for the B-type person. The B-type person has B-type antigens, which you can see here as the triangular spikes, but its antibodies that it doesn't have is going to be made against what it doesn't know. It doesn't know what A-type is because it never grew up with that. And so it makes antibodies against what it doesn't know. In this case, the A-type antigen. A person with AB has both the A-type and the B-type. So it doesn't make any antibodies at all because its immune system grew up with both. I know what A looks like and I know what B looks like. And then an O-type person doesn't have either of those, A or B. So for them, they make antibodies against both. They don't recognize A, so they make an antibody against it. They don't recognize B, so they make an antibody against that. So they make antibodies against both. So then when you're taking a look then at blood typing, you have to make sure that your blood type matches. Why? Because ultimately, if a type A person makes antibodies against B, and a B person makes antibodies against A, and an AB person makes none of these, and an O type makes both, then typically the antibodies are going to cross-react depending on who you transfuse with, right? So for instance, during a blood transfusion, if the antibodies in the recipient, like me, for instance, if I were getting a blood transfusion, sees an antigen that it doesn't recognize on the surface of the donated blood, then what's going to happen, my antibodies are going to attack that blood, clump it up, and then that's going to cause a problem, right? So for instance, a type A person cannot get type B blood. Why? Because they make antibodies against type B. If I have type B blood in me, my immune system will attack it because it's foreign to my body, right? Same thing for a B-type person. A B-type person can't receive A or AB. Why? Because of that A piece. That's the foreign part, right? An A person can't take AB. Why? Because of the B part. That's foreign to me. But an AB person can take both, right? For instance, type AB can basically take it from all of them. They're called a universal recipient. A type O person can only receive blood from an O-type person because A is scary to them and B is scary to them. As a result, they can also donate to everybody, which causes them to be the universal donor, right? So when we're talking about cross-matching, we're looking to see and to make sure that we don't get any agglutination. Because what's going to happen is if I've got blood cells with the A-type antigen on it, and I happen to mix this with the A-type antibody, then my A-type antibody is going to basically bind to what it recognizes, which is this antigen. And what's going to happen is it's going to grab onto all these red blood cells and clump it up. This is agglutination. It tells you what's there. Right? So this is kind of what's happening, right? So here's your situation. So if you have an A-type blood donor who makes anti-B antibodies, then what's going to happen is the recipient, right? So, which is A-type, is not going to see its A-type, right? Because these are all A-type. So it's looking for what it doesn't know. Remember, this is anti-B. That's what's in the recipient. Now, if we have an A-type donor with a B-type recipient, now all of a sudden the B-type is making what it doesn't know, which is the A-type antibody. So when you mix them together, the antibody is going to attack the blood of the donor because it doesn't know it. However, there's another component to blood grouping, right? Because we also have the positive negative piece. So the Rh factor is another type of antigen. It's another glycoprotein, and you either have it or you don't. So if it's on your red blood cell, then you are Rh positive. So we'll kind of put a little square on here. If you don't, then you're Rh negative. So in this case, this is typically only develops once you're exposed to the Rh factor. So it's a little bit different than ABO, but it's kind of a similar sort of a thing. But the important thing is with Rh grouping, the way we found this is because we discovered that there's something called the hemolytic disease of the newborn. And this is essentially when a woman who is Rh negative gives birth to a fetus that's Rh positive. So what happens is the fetal blood mixes with the mother. And so the fetus has this strange looking protein on its surface that the mother's immune system has never seen before. And as a result, because it's foreign to her, then what she does is she makes antibodies against it and she goes to attack it. So the mother's system is actually attacking the baby's blood. And so typically speaking, it usually doesn't happen in the first birth. It usually comes along with the second one because the mother's immune system is now aware of it. And then what happens is the antibodies can cross the placenta and they attack the fetus's red blood cells. And this leads to anemia, disabilities, and if it's really extreme, it's death. Generally speaking, they have to administer kind of a slight immune suppressant to the mother called Rogam. And so this is kind of like an antibody. So, and this will happen shortly around the birth time. So just to make sure that the mother's immune system is not attacking the baby to death. So this kind of what it looks like. So you can see the baby's on the first infection, the baby's blood is mixing with the mother's. The mother sees it and starts making antibodies. And the second one, the antibodies are ready to go. And so they can cross the placental barrier and start attacking the baby's red blood cells. Okay. So now let's take a look at our last topic, that is homeostasis. So we take a look at homeostasis. Basically, the entire body is going to be cooperating together for homeostasis. So you have cardiovascular disease, digestive, urinary, muscular, skeletal, lymphatic, all cooperating together to basically generate internal conditions that are constant and stable. And so they interact with each other and with the cardiovascular system. We talked a little bit about that in the last chapter. And like the cardiovascular and the lymph systems work together to basically regulate the interstitial fluid. That's the fluid of the tissues to make sure that your blood plasma is well hydrated and that the capillaries absorb any leftover fluid in the tissues. And then, of course, that gets returned back to the cardiovascular system. The respiratory system interacts with the cardiovascular system to deliver oxygen. So the respiratory system will pick up the oxygen, the cardiovascular system will deliver it. Also, it interacts with the digestive system for the delivery of nutrients. So that the digestive system will absorb the nutrients and the cardiovascular system will deliver the nutrients. The cardiovascular system will also interact with the muscular system in order to provide blood and nutrients. So, for instance, your cardiac muscles certainly contracting and circulating blood throughout the body, but your smooth muscle, which is associated with your organs, they need to contract and relax. And so ultimately, they are maintaining the vessel diameter. Um, and so that's part of blood pressure. So those muscles are interacting. Skeletal muscle contraction is essentially we took a look at that, right? Because ultimately this was part of that venous blood return when you had the skeletal muscle contraction in order to get blood return back to the heart. So you can see how there's interactions between the muscular system as well. The cardiovascular system interacts with the skeletal system because in the bone marrow, which is part of your skeletal system, this is where you're producing your red blood cells and, of course, also your white blood cells. And also, calcium, which is essentially packed into the skeletal system, is necessary for contraction and blood clotting associated with the cardiovascular system. The endocrine system, which is your hormone system, is also important in regulating not just the other parts of your body, but also blood cell production and calcium release, which you need for blood clotting, and also you need that for cardiac muscle contraction. And then, of course, the urinary system, in the sense that basically this allows us to maintain salt water balance and osmotic balance. But also, this is where erythropoietin is coming from, which is the stimulator or the hormone that essentially is telling our red blood cells to produce from the bone marrow. And so that basically is the lump sum of chapter 6.